For our last module today, we're going to be covering a combination of Gen Chem review material and also introducing some new specifics about how to convert between concentration units using dimensional analysis. So remember that coming to grips with the definition of concentrations and how different units and ways of expressing concentrations and how they relate to each other may seem relatively trivial on the surface. But since analytical chemistry and quantitative analysis specifically is primarily about which chemical and how much, being able to accurately and precisely define concentration and understanding how you can use the definitions of one set of concentration units to convert a concentration measurement into another set of concentration units is an incredibly fundamental skill in analytical chemistry. While concentration measurements may look very familiar, may look very trivial on the surface, and you say, yep, I've seen that concentration unit before, I've got it. Being able to convert between different concentration units is one of our early and most fundamental skills this term, and it's one I expect you to be able to carry out throughout the rest of the quarter. So particularly when we get to the next module where we talk about how to convert from one concentration unit to another concentration unit, make sure you're buckling down and you're really seeing the big picture, and you can accurately chart a path to, say, convert from a concentration measurement made in ppm to a concentration measurement made in molarity. All right, again, we're going to use the measurement of lead in drinking water as kind of our jumping off point here. So as I mentioned in a previous module, the mean lead concentration of Flint River, Michigan drinking water in 2014 was found to be 10.6 plus or minus 3.7 parts per billion for a specific 100 household sample taken in that year. In the previous modules, we've talked about how we break down this measurement and understand how the reported measurement is constructed, in the sense that the average lead concentration comes first, followed by plus or minus the standard deviation, and then the concentration units. In this module, we really want to zero in on the concentration units and understand what they're conveying to us. And right away when we look at this, this is a concentration unit that you may or may not have heard of before. It's certainly not one that chemists use in the laboratory very often. So units, of course, express how your concentration is actually being scaled. And a concentration measurement reported without units is next to useless, because if you can't tell what scale the concentration is being measured on, the number doesn't actually mean anything. The standard chemistry boilerplate announcement: report all your measurements with units. If you're not reporting your numbers with units, they don't count. But what does this ppb really indicate? Well, ppb is a unit abbreviation that stands for parts per billion. And in this module, we're really going to get into what parts per billion means as a definition of concentration, how we could convert from a parts per billion measurement to a molarity measurement, or vice versa, and why in a given situation you would choose to measure a concentration in parts per billion instead of molarity. But never lose sight of the fact that no matter which unit you're using to measure concentration, concentration units really always convey the same basic type of information. Because concentration is a derived SI unit that expresses an amount of a solute in a volume of space, all concentration measurements boil down to how much stuff is in what volume of space. Your challenge is to understand how that amount of stuff is being expressed and how that volume of space is being expressed. And that's what this module is all about. So the key skills I want you to be able to take away from this module is, if you haven't gone back and reviewed your SI units and prefixes and you feel it all shaky on those, definitely review those, because units and prefixes are going to be really key in terms of how we express concentration. Make sure you're still feeling good about using unit conversions and dimensional analysis to convert between measurements, because that's going to be at the heart of how we convert between different equivalent concentration measurements. We're going to introduce you to 4 concentration units specifically in this module, which are molarity, molality, parts per million, and parts per billion. Hopefully most of those should be a review for a lot of you. If they're not, that's okay. We're going to go through them kind of from first principles, but brush up on your concentration units. If you have your Harris textbook, get in there, look those up, and your assigned reading for this section will parallel section 1.2 in Harris Quantitative Chemical Analysis. Aside from the names of the concentration units that we just covered, and again, I hope that most of those are going to be more of a review than an introduction to new concentration units, the only new vocab that we want to introduce here or have you review is the basic terminology associated with chemical solutions. So that's solute, solvent, and solution, in addition to the concept of concentration. And this is our first stop, is we want to talk about what is a chemical solution and how do you make a chemical solution. Well, remember that solution is just a technical term for a mixture of chemicals. When we're talking about quantitative analysis, very often when we say a solution, we mean an analyte, which could be a liquid or a solid, dissolved in a solvent like water or ethanol or some organic solvent. But the term solution can apply to any mixture of chemicals, including gas phase mixtures of chemicals. And so in terms of the broadest possible definitions, when we talk about solutions or chemical mixture, the solution is the mixture of two or more chemicals. And it must be a homogeneous mixture, so everything must be well dispersed, can't be lumpy, can't be heterogeneous in its composition. And we're going to treat our chemical solutions as composed of two parts, the solute and the solvent. The solute is whichever chemical is the minority component of the solution. So whichever chemical there's less of in solution, that's the solute. The solvent is whichever chemical there is more of in the solution. And again, generally from our standpoint, that's going to mean that our solvent is usually going to be the liquid phase, water, ethanol, or an organic solvent. And the solute is going to be the chemical that's dissolved in. Right, so the most common picture would be to look at sodium chloride dissolved in water. Sodium chloride is an ionic compound which dissociates or breaks apart into sodium +1 and chloride -1 anions when you dissolve it in water. And so when you think about your basic solution, if you have to reground yourself in terms of solution, think about salt water. Sodium chloride is your solute, water is your solvent, together they're a solution. And we can use the term chemical solution, again, to describe any mixture of chemicals, whether it's only 2 components, or it's 3 components, or it's 50 different chemical components. A couple other examples of solutions that are relevant to our discussion would be a solution of caffeine in water, where caffeine is the solute, water is the solvent, and together they form an aqueous solution of caffeine, where aqueous, again, as a general chemistry term, just means a solution where the solute is dissolved in water. Or in the case of our Flint, Michigan drinking water sample, lead is the solute, water the solvent. Together you have a solution of aqueous lead. So keep those terms straight, and from an analytical chemistry perspective, generally when we refer to the solute, we'll be talking about either an analyte, which is more likely, or potentially an interferent. The solvent and any interference together would be considered the matrix in most cases. And then the solution is the total package, the analyte dispersed in the matrix. So that's kind of how the terms for solutions, solute, and solvent that you learned originally in general chemistry map onto our new vocabulary of analyte and matrix. And since concentration of solute in solution maps so nicely onto concentration of analyte in the sample, we're going to look now at several different definitions of concentration units and talk about how they would be used in an analytical chemistry context, how they're defined, and ultimately how we can interconvert between them. And it's worth, again, reviewing these different types of concentration measurements, because part of the job of being an analytical chemist either work in a field every day where you interact with other scientists in different fields who have different preferences for how they measure concentration units, or you often act as a go-between between laboratory chemists and people in other disciplines where you have to translate what different concentration units mean from one group to another. And so we're going to start in a familiar place. We're going to start with molarity, which is the chemist's favorite unit, for reasons that we'll elaborate on here in a second. So molarity, a concentration unit which is abbreviated capital M, describes the concentration of a solution as moles of a solute per liter of solution. Recall that 1 mole is Avogadro's number of anything, and so if you're looking at how this derived concentration unit is constructed, 1 molar, which is how you say the unit molarity, you say it molar, is 1 mole of the solute per liter. The general way we've learned to write molarity as a concentration unit more explicitly in general chemistry was to say a mole per liter. But now we have to peel back the layers a little bit more, and it's going to be really useful to say a mole of what per liter of what, particularly when we need to convert molarity to other concentration units. And remember, fundamentally, molarity is a mole of solute per liter of solution, not per liter of solvent, because both the solute and the solvent take up space. The volume in the denominator of molarity indicates the total volume of solution, not just the volume of the solvent itself. In a very dilute solution, those numbers turn out to be kind of the same, but you can't assume that they're the same. So get into the habit now of when you start reporting molarity, go from, well, a 1 molar solution of hydrochloric acid is 1 capital M HCl. That means there's 1 mole of HCl for every liter of solution, where the solution is the HCl and the water together. And that's really important to write the definition that way for reasons we'll see with a little more clarity here in a second. Why is this chemist's favorite concentration unit? Well, obviously when we're talking about predicting reaction yields and how to prepare solutions, mole of solute is in the numerator and total volume is in the denominator. So for chemists who think in moles, this makes solutions very easy to prepare. But for toxicologists, environmental scientists, and other non-chemists that analytical chemists have to work with when they're talking about analyte concentration, much of the scientific world doesn't use molarity as their preferred unit of concentration. And so while we as chemists tend to think in molarity as a concentration unit, we now have to get familiar and reflexive with using other equivalent ways of measuring concentration so that we can report our analyte concentrations in such a way as to make the most sense. You're probably introduced to at least one more concentration unit in general chemistry, which is the molal, measuring concentration on a scale called molality. 1 molal, which is abbreviated with a lowercase italicized m. I know that's confusing and it makes it look a little bit like meters, but even in science there are only so many symbols we can use in the world. So unfortunately the abbreviation for the concentration unit molality looks like an italicized m, which makes it look a little bit like meters. There's definitely a concentration, not a length. This is a more obscure unit of concentration which is primarily used in predicting the magnitude of colligative property changes. So for instance, in general chemistry, when you talked about freezing point depression, boiling point elevation, surface tension, osmotic pressure, you started to use molality because molality is the concentration unit that most directly connects amount of solute to how much it changes the colligative properties of a mixture. In analytical chemistry, we only use molality as a concentration measurement in very specific circumstances, but for now, as long as we're reviewing concentration units, we still expect you to be fluent in the molal, just as fluent in the molal unit of concentration as you are in the molar unit of concentration. The fundamental definition of molality is a little bit different from molarity in the sense that 1 molal is 1 mole of solute, so the numerators look the same, but the denominators are different. Molal expresses concentration as amount of solute per mass of solvent, which is fundamentally different than molar as a concentration unit. So 1 molal is 1 mole of solute per kilogram of solvent. And again, it's going to turn out to be really useful to write this out explicitly, not just 1 mole per kilogram, but 1 mole of solute per 1 kilogram of solvent. Therefore, a 1 molal solution of hydrochloric acid means that you would have 1 mole of HCl for every kilogram of the solvent water, which was part of the mixture. We have 2 more related concentration units to introduce. I'm going to introduce them to you very generally, and then I'm going to kind of gloss over these first ones and talk about how they relate to the concept of ppm, parts per million, and ppb, parts per billion. So the other way to express a concentration is much more common in engineering and environmental science than it is in kind of a synthetic chemistry laboratory. And these are measurements known as the weight percent and the volume percent. On the surface, these are very straightforward ways of measuring concentration. Weight percent as a measure of concentration simply ratios the mass of the solute to the total mass of the solution. And then you multiply by 100% to make it a percent. So if you're talking about a weight percent, and you see that something is 5% by weight ethanol, that would mean that there are 5 grams of ethanol for every 100 grams of solution. So your weight percent is always mass of solute divided by the total mass of the solution. If you had a 95% weight percent solution of ethanol, that would mean that there are 95 grams of ethanol divided by 100 grams of solution. In this case, we'll say that the solution together is simply the ethanol plus some remaining water. So it's 95% ethanol, it's 5% water, solute mass divided by solution mass. Incidentally, 95% ethanol is essentially the highest purity to which you can distill ethanol. It's actually pretty hard to separate water and ethanol by distillation. So a 95% solution of ethanol is essentially the highest purity of ethanol you can actually make. Otherwise, too much of the water stays around unless you are very, very careful with your distillation procedure and you have the right apparatus. So notice that if you're talking about a weight percent, to indicate that this is a ratio of the mass of the solute to the mass of the solution, after the percentage of the weight percent, you often see in parentheses W:W for weight to weight. Because you can also describe solution composition as a volume percent instead. And densities provide you a means to convert between these two measurements, which is something we'll cover in the next module on Monday. Volume percent can be defined the same way as weight percent, where volume percent is the percent of a solute in a solution by volume. So a volume percent is the volume of your solute divided by the total volume of your solution times 100%. Same basic concept, but we're using a volume to volume comparison as opposed to a mass to mass comparison. And so one thing that should click fairly immediately is for most chemicals, you can describe a weight percent and you can describe a volume percent. And even though the percent number looks the same, that's not the same concentration. So you have to be explicit and use that parentheses percentage sign V to V or W to W to indicate that when you're giving a percent composition, whether it's based on mass or it's based on volume. But in terms of the basic idea, still really straightforward. If you're talking about a 5% volume to volume ethanol solution, like a beer, that means that there's 5 mils of ethanol for every 100 mils of total solution. For right now, we're keeping our life simple and saying that the total solution is 5 mils of ethanol for every 95 mils of water. But when you're talking weight or volume percent, mass or volume of solute on the top, total mass or total volume of solution on the bottom. So you could write this 5% ethanol solution as either 5 mils of ethanol per 100 mils of solution times 100%, or if you wanted to be a little more explicit about the composition, you could say 5 mils of ethanol per 5 mils of ethanol plus 95 mils of water, as I've done here. And thinking very precisely and accurately about the composition of these solutions is the first step to being able to convert between these different concentration measurements, which is where we're going next. Now, in analytical chemistry, unfortunately, we often use percent compositions. I say unfortunately in the sense that this adds a little bit to the learning curve for incoming students, but it's actually a very useful way to do things. Because analytical chemists are so often detecting low concentration or trace amounts of an analyte in a mixture, weight percent and volume percent themselves are not often very convenient ways for us to express the concentrations of the analyte that we're measuring. Particularly when we're dealing with environmental samples, the concentration of the analyte is often extremely low, and so there's not a large amount of mass of the analyte compared to the total mass of the solution. As a result, that doesn't make weight percent itself or volume percent itself a very convenient way to express analyte concentration. So when we're talking about an environmental sample, like lead in water from our Flint, Michigan drinking water, we use a variation on weight percent, which is parts per million, ppm, and parts per billion, ppb. Parts per million is another way of expressing weight percent, but it's much more useful for low concentration samples. And a parts per million is a weight percent or a volume percent that expresses concentration as a gram of solute per million grams of solution instead of per 100 grams of solution. So it's the same construction as a weight percent, just better adapted to very dilute solutions of the solute or the analyte. So for instance, if you saw a concentration measurement that was expressed as 5 ppm calcium 2+, well, the solute you're looking at is a calcium 2+ cation. The ppm is the abbreviation for parts per million, so these P's, parts per million. The little p in this case does not indicate pico, which is an SI unit prefix, so it can be a little confusing the first time you see it, but pp stands for parts per. Parts per million is ppm. And what this means as a weight percent is that there are 5 grams of calcium for every million grams of solution, not for every 100 grams of solution. And also notice that parts per million is not expressed as a percentage, it's simply the ratio. A 5 ppm calcium ion solution is 5 grams of calcium ion for every million grams of solution. Or put another way, 5 grams of calcium for every 999,995 grams of water plus 5 grams of calcium. That's the solution together. It turns out, as we'll show you in our last piece today, that because the density of water is 1 gram per mil, for dilute aqueous solutions, we can actually express ppm with an alternative set of units, which reads as milligrams of the solute per liter of solution. But for some particularly toxic or particularly hazardous chemicals like lead in drinking water, parts per million is not still a great unit choice to express the concentration of a very, very dilute solution. So we pull out ppm when we have a solution concentration that is essentially too dilute to express effectively in molarity or as a weight percent. If the solution is very, very, very dilute, what we would call trace, instead we use another variation on the weight percent, which is parts per billion, or ppb. This works exactly the same way as parts per million, but instead it's for even more dilute solution. How much more dilute? About 1,000 times more dilute than a ppm solution. In this case, parts per billion is effectively a weight ratio that expresses the concentration of the analyte as 1 gram of solute for every billion grams of solution. So if you have a 5 part per billion calcium solution, ppb, part per billion, first off, that should register that that is 1,000 times more dilute than a 5 part per million calcium concentration. What that means is there are 5 grams of calcium ion for every billion grams of solution. So 1 followed by 9 zeros, billion grams of solution. Or put another way, 5 grams of calcium for every 999,995 grams of water plus 5 grams of calcium. That's the total solution. So parts per million is used to measure analyte concentration in very dilute solutions. Parts per billion is used to measure analyte concentration in even more dilute solutions, what we would consider to be trace or ultra-trace amounts of the analyte. And once again, there's another alternative way. Once again, we're going to see that there's an alternative way of expressing the units associated with a parts per billion measurement based on the density of water. So for extremely dilute solutions, parts per billion can also be expressed using an alternative unit notation, which reads as micrograms of solute per liter. So you see that abbreviated as a Greek letter mu, lowercase g, divided by capital L for liters. And remember, in SI unit systems, the prefix micro means 1/millionth. So a microgram is 1/millionth of a gram, or 1 times 10 to the negative 6th times a gram. We're going to show you how we can come up with this alternative statement of units here in our last activity today, where we'll start to build the skills you need for converting between concentration units, which is something that we'll follow up with on Monday when we pick up again. But the big takeaways, remember, we've introduced you to 4 concentration units today, 2 of which are probably relatively new to you. Coming away from this lecture, you want to be really fluent in molarity, molality, parts per million, and parts per billion, and the post-lecture exercises, which will be your first post-lecture exercise, which is worth some points today, is going to follow up and make sure you understand the differences between those definitions. Remember, if you have any questions, because this is kind of simple looking material, but it does take some practice, if you have any questions, please hit me up on Zoom during office hours, or I'll be online live on Zoom during normal class times, so you can duck in and out of these pre-recorded lectures to ask me questions and clarify specific points. One of the challenges of learning when we can't get together in person. So if you have any questions, please do look for me. I'll be happy to answer them. Make sure you get to those post-lecture exercises. We have one more tiny module to do today. That's the last order of business, and after that, I'll see you on Monday.